Hello, everyone, and welcome to another edition of an OWASP meeting. So this is another meeting in collaboration with OWASP Suffolk and OWASP Dorset. For those that, let me share first my screen. I have a little bit of a presentation. Okay, now you should also see my screen. So like I said, this is a joint event with Dorset and Suffolk in collaboration. And here are the chapter leaders of the Suffolk and Dorset. We have also David Flint online and my co-leader, Craig Francis. So for those that are new, the OWASP is basically about improving the security of the software. It's a non-profit organization which is worldwide, and we have more than 200 local chapters all over the world. It's all about improving the security, the community. The OWASP community is about sharing new sharing materials and documents about the OWASP to help everyone out there to develop software in producing more secure software. We have projects like tools, and we have documentations to help everyone. All of those are free or are under a free license type of software, free software type of license. This event, the chapter events, are free for everyone to participate in. However, our conferences are evidently not free. So those would be the conferences where we actually bring leaders in security from all over the world to speak and share their knowledge. Talking about the events, the next coming event at global level is the OWASP Global AppSec, which is in San Francisco in November. And this November, so you can still buy the tickets if you fancy. And in terms of the next events as organized by ourselves, the next one is organized by OWASP Suffolk, which is OWASP Fight Club. And as we have Dave on the line, maybe I'll invite David to actually say a couple of words about this. He has a couple of events already lined up, so I think it would be good to actually have him talking about the next events. Dave?
Yeah, thanks, Katie. So the Fight Club is kind of aimed at anyone that wants to learn a bit more about ethical hacking. The next one we've got on the 25th of October will be sort of taking a step back and walking through how to sign up for Hack the Box and how to attack a simple box. So it's kind of one for our beginners on Tuesday. So it's Tuesday and start at normal time on the usual channel.
Excellent. Thanks a lot, Dave. The next one is another interesting one. It's organized by OWASP Dorset, where Mike Werner, one of the chapter leaders, is actually going to speak about deepfakes, a growing cybersecurity concern. So, and then we have the next event from David, which is on the 22nd of November, which is Introduction to OSINT. So for those that are actually looking for this new concept, then this would be a great event for them to actually participate in. And tonight's speaker is Kevin Sheldrake. So I met with Kevin some time ago. I think it was in Vienna, David, Kevin?
That's right, yes, yeah. DeepSec in Vienna.
Yeah, we met there where we had another interesting talk, and since then we kept in touch. To put it simply, his researches are pretty awesome. And he actually has a new research. This time is around eBPF, And I think it would be a benefit for everyone to start understanding what are the security concepts into this new environment and how we can actually make better of them. So I'll stop sharing now and I'll have Kevin taking over.
Okay, so let me see if I can. Right, hopefully you can see a slide. Yes?
Yes, we see it. It's the one which is it is actually the slide. Yeah, that's which says the eBPF.
Okay. Right. So yeah, so my name's Kev, and I work for iSurveillance, and I make things in eBPF. But first of all, I was just going to, talk about my lockdown experience, because I really enjoyed lockdown. I got to work from home and do a lot of fun things. So I made a bookshelf door. So that's the door to my spare bedroom. You can put a book, and the thing opens up. That is quite a project. I bought a piece of art that which was on the background behind me. I don't know if you all saw, but that's on my wall is a former police riot shield that's been painted up by Jimmy Corty, formerly of the KLF. They were selling them at Banksy's Dismal Land, and but I bought this online. And I also started a master's degree, a Master of Research degree in psychological methods at University of Sussex. Taking advantage of the lockdown where all teaching went online and went remote, I contacted one of my heroes in the world of hypnosis to ask if I could study with him, and he said yes. So I'm halfway through a 2-year part-time master's studying with him. We're about to start doing experiments for the next academic year, which will be really exciting. And I'm hoping after that to then go on and do a part-time PhD with him to truly fully understand the wacky world of hypnosis. I also got married to my wife, now wife. We were married about a year, and between us we started a blog called Cosmic Pancakes. That's cosmic-pancakes.com, which is all about the wonderful world of hypnosis, where we write sarcastic book reviews about all the crazy books that exist in that world. I would review some academic books and talk about science, and we have a lot of fun. So if you get a chance, do come and have a look at our website. We're when we look at our demographic or our geography of our readers, the major hotspot is in Langley, Virginia, which is, as we all know, the home of the CIA. So if it's good enough for them, then I'm sure it's good enough for you. But I'm here to talk about eBPF. So this is just a slide of where I've been in my career, and my Twitter handles. Kev Security is my work handle, which is where I talk about eBPF and things like that. Not very much, very low traffic. And Kev Sheldrake is my personal one, where I talk about hypnosis and politics, and other ranty type things. So choose the handle you want to follow if you want to follow them. Before I worked for iSurveillance, I worked for sysinternals at Microsoft, which I'm sure everyone is aware of as a brand. They make and maintain about 80 tools, freeware, most of them on Windows. And I ported the biggest and most complex one of those, which is Sysmon, from Windows to Linux, using eBPF to replace the Windows driver. So if you don't know, Sysmon has a Windows driver which collects events, collects information, sends it to a user space part of the tool, which runs as a service on Windows, and that's turns that information into events that goes into the event log. So on Linux, I ported the user space version across, and in fact, the Windows and Linux versions share that most of that portion now, and open sourced it. And I replaced the Windows driver with eBPF programs to collect the information, and that was really exciting, really fun. And shortly after releasing that, I ended up talking with iSurveillance, and things changed, and I kind of got a job with iSurveillance, where I build a similar but much more advanced thing. So I'll talk about eBPF. I'll talk about the good, the tricky, and the vulnerable. It's not really the good, the bad, and the ugly. But it is the good, the tricky, and the vulnerable. So mostly it'll be about the good. There quite a lot of stuff on the tricky, and a little bit about vulnerabilities towards the end. So if you've used T-Shark or Wireshark or TCP dump or anything along those lines, then you've used classic BPF, which stands for Berkeley Packet Filter. Essentially, if you imagine writing the packet capture part of Linux back before this existed, then you could you could build a filtering logic and a configuration logic so user space can tell the kernel what kind of packets you want to capture, because you don't want to capture all the packets and send them all to user space, because that would be massively wasteful of resources. You need a really big fat pipe to get all the data to user space. So you want to do your filtering in the kernel. But if you wrote a filtering engine based on a configuration, then you would be limiting yourselves to only the types of things that you dreamt up that you might want to filter on. And if you then changed your mind, you wanted to add new ways of filtering things, then you'd have to change the kernel. And changing the kernel is a slow process, and that still wouldn't be available for the kernels that you're probably running on, or your customers are running on, or the machines that you're sat on are running on. So instead, what they did was they came up with this Berkeley Packet Filter, which is essentially a virtual machine that runs inside the kernel. And your filter, so in this case, -INE, not port 22, so any interface and everything that isn't running on port 22 or either send or receive, is compiled into a BPF program, and it's inserted into the kernel at the point where it sees the packets. And for every packet it sees, it runs the program, and the program says yes or no at the end of it to say whether or not user space wants the packet. And if user space wants the packet is sent to user space from where it can be displayed or whatever. So it's quite powerful. You can do lots of things with that, obviously. eBPF, which started out life as extended BPF, but no more. It is now just the letters eBPF with a nice B logo. It takes that idea and says, why don't we attach those programs anywhere in the kernel, any function, any trace point, any network operation, etc. And let's expand on what we can actually do with those, with that programming. So rather than being a filter that says yes or no, maybe we would be able to access some internals of the kernel. Maybe we'd be able to send arbitrary data back to user space, and that those programs would run in a VM inside the kernel. So it's seen as the biggest change in kind of Unix for 50 years. So let's talk about it. As I say here, it's revolutionary technology. It's massive, which is why I'm kind of talking about it. So the image here is kind of showing you when your user space program wants to get access to some resources, write a file, send a network information, fork or whatever. Typically, it's done by using a syscall, a system call, and when you do that, those system calls exist as functions in libc. libc calls a particular system call architecture, which switches the task into the kernel. The kernel does stuff to get you that resource, and then it returns back to user space via libc, and that returns the information or the answer or the return code or whatever back to the application. So when you run your programs, every time you access a file or access the network or whatever, you're causing stuff to happen in the kernel. Well, we can attach to those points. We can easily attach to syscall entry and exit points. We can attach to the start and end of the entire syscall architecture or syscalls individually. But we can also attach to any other function in the kernel. And when that point of execution in the kernel hits the point where we're attached, the kernel process stops and starts to run our code instead. And when it's finished running our code, it returns back and the kernel continues. So we can observe all sorts of things. And as I say, it runs in a virtual machine. So we're not running natively like a kernel module. We're running, inside a constrained environment. The claim is like it's JavaScript inside a browser, as an example. We can have we can share data structures between programs, BPF programs that you can load multiple BPF programs at once, and we can share data structures between them. We can also share those with user space. And we have a ring buffer. In fact, there's more than one ring buffer now, but there's ring buffer, which we can use to send data between the kernel BPF programs and the user space. So we can stick stuff in and it pops out in user space, which lets us get access to things. So what might you want to do with it? If you've ever used strace, that literally traces syscalls. You strace a program, and every syscall it calls, strace will print out the syscall and the arguments and the return value. Well, sometimes your arguments are quite big, like they're massive buffers, and strace truncates that and only gives you certain information. So you could rewrite strace really simply in BPF and make it print out what you wanted. You could target certain things. So you could have logic whereby it doesn't strace or print out all the information until a certain event happens, a certain thing. It sees a certain syscall or certain piece of data or after a certain period of time or whatever, and then prints out more information. You could make it richer. You could dump information from the kernel, which strace doesn't do. You get additional state, for example. We can not just attach to kernel functions, we can attach to userland functions as well. So we could snoop on readline in libc, for example, or wherever it is, libreadline, or snoop on the OpenSSL read and writes and see the data that's being sent to those functions or retrieved by those functions, which obviously with OpenSSL means that we're defeating encryption just by sitting on it. So these are the sort of things that in the past I would use ptrace to do, which is the debugging infrastructure underneath things like GDB. But instead of using ptrace to attach to a process and then break on certain instructions, we clamp ourselves on top of it and we're outside of the process, but the same kind of things happen. But we're we're detectable in different ways. With ptrace, a piece of malware could detect you ptracing it and stop you from ptracing it. That's much harder with BPF. Looking bigger and into the enterprise, secure container networking. So basically, if you use Kubernetes, for example, then you'll know that there are various ways of networking the pods in Kubernetes. So started out with kubeproxy, which is based around IP tables, went to IPVS, went to sidecars where you had extra containers alongside your containers to proxy the information in and out, things like that. Well, you can replace all of that with Cilium, where we do all of that routing in the kernel in BPF programs. The benefit of that is it's fast, really fast. So if you want fast container networking, go find Cilium. It's open source. You can get it on GitHub. If you want to use it, and if you want to spend money to get all the extra bits and pieces that we make, then we also sell an enterprise version. Also, auditing. Tetragon is the thing that I work on. Again, open source. You can go find it on GitHub, and again, there's an enterprise version if you want to spend money and get extra bits. It's we can do all the sorts of things that you could do with K-Audit or Audit D. We can see things happening and we can report on them. Sys1 for Linux, which as I say, I ported over at Sysinternals, is in a similar sort of space, but that project is kind of stalled a bit when I left. But it's open source. Anyone can go and add to Sys1 for Linux in the same way that they can add to Tetragon or Cilium. But one of the reasons why we might want to replace K-Audit or Audit-D is that Audit-D and K-Audit are not container aware, and they're probably never going to be container aware, which means that the information that you get out of it is from the base operating system perspective. And what you probably want are the process IDs and user IDs that are from within the containers, as opposed to the outside view of that. You might also want to know which container, which pod something happened in, which K-Audit is never going to be able to give you. So there are lots of good reasons for wanting to move to something that is container aware. Sys1 for Linux isn't container aware yet. It was always planned, but Tetragon is by design. So Tetragon is a great solution. And the other thing you might want to do is build or detect rootkits. And I recommend you go and look at Linux Thor on GitHub. He spoke at our DEF CON group in Gloucester in the lockdown virtually. Nice guy, been doing some interesting work there. So I definitely recommend going and have a look. Right, so before I get into the technical details, I'll just talk a bit more about speed, because, it's one thing knowing how to use BPF and how to program it, which is mostly what I talk about. It's another reason, it's another thing to understand, like, how fast it is. And so if you were using IP tables, kube proxy for container networking, then the latency increases as you increase the number of services in your cluster. Whereas with eBPF, with Cilium, it's constant. So if you want to scale things massively, then Cilium is a much better solution than IP tables, for example. IPVS, which would be another solution that kube-proxy can use. What you'll see is CPU overhead increases as you increase the number of packets or the rate at which the packets are arriving. Whereas so we can get more packets through with Cilium, with eBPF, than you can with IPVS. And the CPU overhead is, as you can see by that second graph, absolutely minimal compared with IPVS, which is just growing by the number of packets that you have. So BPF is powerful, really, really powerful, and it lets you do lots of really cool things. So Tetragon, just to put it into perspective, can do all the things I talked about on that other slide. We can connect anywhere, we can observe almost anything, and we can send those things to user space as events. And we can do all of that using YAML to configure it. So the rest of this talk is going to be about programming BPF mostly, which is a challenging thing. But what we've done with Tetragon is built a flexible thing whereby you can write some YAML to say where you want to connect, what arguments you're expecting to see at that particular function you've connected to, match on those arguments or do some logic on those arguments, and then do something with the information, send it to user space as an event. We can kill the process, and various other things. So if you want to make use of BPF for observability, then Tetragon is going to really help there. But oh yeah, and I forgot, yeah, if you want to play with any of this technology, like, we have labs that are free. You just got to sign up, and then you can get into a already set up lab and start playing and see how to configure it, what it does, and those kind of things. Right, let's talk about some technical stuff. As I said before, it runs in a virtual machine, and that virtual machine is basically a RISC kind of architecture. So there's a load of registers. Some have preferred functions, but they're mostly general purpose registers. And we have all the normal kind of machine code instructions you'd expect in a RISC architecture. So you can read and write memory, you can do arithmetic, and you can do conditional jumping and the likes. The idea of the instruction set is that it will map easily to any modern processor. So there's practically a one-to-one mapping to x64, for example, and the similar to ARM and probably to other processors, which means that you can JIT compile BPF programs really quickly, really easily on the fly. And you're getting native instruction speeds out of BPF. So it's not like well, JavaScript in a browser being a great example. Your JavaScript is interpreted and it has to be kind of JIT compiled down to machine code. Well, this is much more of a one-to-one read across. So it's more of a translation than a compilation. So it gives you native speed out of the kernel as opposed to something that's interpreted, for example. The memory model is really interesting. You only have 512 bytes of stack, and that seems really small, and it is. But because you don't really have function calls, depending on which kernels you're supporting, obviously, which I'll come to, and there are no global variables, then almost all you've got on the stack are local variables. And I say there's no heap either, and there's no globals. So it's a bit odd. But what we do have are maps. And these are various different types of kind of memory that you can get access to. So arrays are really obvious. You tell it how big your object is and how many entries you want your array to be, and then you can access those entries, and those can be, and these can be shared between BPF programs and shared with user space. We have native hashes. So if you were kind of storing IP addresses that you'd seen, you could hash an IP address and count against it, for example. You can have these as per CPU and system wide. So one of the things you might want is some heap memory, right? So if you wanted to build an event that's bigger than 512 bytes, you obviously can't just have a struct on the stack because it's too big. But what you could do is store that struct in the first entry, the 0th entry of a per CPU array. And when you need that heap, just ask for the 0th entry of that array. And if you've got multiple CPUs and each one happens to be running the same BPF program, happens to be doing the same thing at the same time, each one would get its own version of that 0th entry. So they won't clobber each other, they won't be racing against each other. And you can use that as heap. So you could put you could make that entry like 64K in size, for example. And when you go and ask for that entry, you'll get a pointer to a piece of memory that's 64K in size, which you can then just use arbitrarily as if it's heap memory. So that's kind of cool. But there's also system-wide versions of these. So if you were storing I don't know, information about IP addresses that you've seen, you probably want to store that on a system-wide map so that whichever CPU sees the packet that you're going to record, they're all writing into the same central database. There's lots of other types of maps as well that I won't go into, but one that's kind of important is the ring buffer, which you push data into, and as I say, that then sits in the ring buffer until it's read out. And you can read it back out in BPF, but usually you're kind of reading that back out in user space. And that's how you get events. So imagine that you're attached to some function in the kernel where something happens. You record a load of information about what's just happened, you into like some heap space inside like an array, and then you sling that entry of the array into the ring buffer, and your user space program's polling that, and it sees it arrive, and then user space now has that information about what just happened in the kernel. That's kind of the model. So where can you attach? Well, you can attach in loads of places. We'll start with talking about trace points. So if you don't know, /sys/kernel/debug/tracing/events has virtual directories for a whole load of classes of events. Oh, I've just realized I'm going to normally I would be using these slides as a slideshow, which is a bit tricky to do while I'm using Zoom. So it's possible that things are going to be all over the top of each other, but we'll see how readable it is in a second. But anyway, so some of these classes that are quite interesting. Net is obviously stuff about networking. There'll be a load of trace points in there within the net subsystem. Syscalls, there's trace points for the entry and exit of every syscall. Raw syscalls has an entry and exit point to the entire syscall architecture that sees every syscall. Shed is all to do with process scheduling, so processes starting up, task switching, etc. Signal is all about sending and receiving signals to processes. So these could be some cool places to interact with. Oh, this isn't too bad. So if you go into one of those directories, one of those virtual directories like syscalls, and in there there'll be sys enter exec ve, for example, and in there will be a file called format, a virtual file, and if you cat that file, it will give you this information, and this information tells you what to expect when your program runs if you attach to this trace point. And what you expect is a struct containing those entries. Now, the first 8 bytes, which is the first box of entries there, is opaque. So even though we know what's in there, we can't access that. And if you try and read anything from that first 8 bytes, you'll get a violation. So you can't do that. But the second box are all the parameters that syscall was given from user space, and the syscall number. Now, the syscall number is quite useful because you might want to attach the same program to multiple syscalls. So exec ve, which launches a new executable, and exec ve at, which also launches a new executable, are very, very similar, but they have slightly different parameters. So you could attach the same program to both those trace points and then check the syscall number to see how to interpret the information that you're given, how to interpret the parameters. And you can see here the parameters are a const char star file name, a const char star argv, and a const char star env, which are literally what you would be given it if you were calling exec from user space. Bear in mind, these are user space buffer pointers to user space memory, which has its own swings and roundabouts, which I'll come to in a bit. But what we can do is we can create a struct based on those parameters, and the one parameter we'll get into our program is a pointer to that struct, where we can just read that stuff out. Actually, I'll talk about it now. One thing that you'll notice if you get into Word BPF is if you do look at user space memory, it's not always available. It's not always paged in. So you might go to read that memory and you might just get back nothing and an error. So often the kind of structure of your program, what you might want to do, or a solution to this, is to have a program attached to the entry point of the syscall and another program attached to the exit of the syscall. And on the entry, store the pointers just as pointers in a system-wide hash, right? And you could hash that based on the process ID and the thread ID, which you can get. And then the syscall, and then exit, and then the syscall would run, and then your exit program would run, and it will be in the same process ID and the same thread ID. Use that as a key into that hash to retrieve those pointers, and then read the memory that those pointers are pointing at. Now, bearing in mind that the kernel has just read the memory that they're pointing at, there's a really good chance that memory is now paged in, and you'll be able to access it. It's not guaranteed, but it's much more of a guarantee than just hoping that it's available. I'll talk about that a bit more later on anyway. A different trace point, so not a syscall trace point. This is shared process exec. So this is a trace point within the shared subsystem, and this gets hit when a process exec VEs, when it runs a new process. So why would you connect here? Well, you could connect both exec VE and exec VE at end up at this trace point. So you could just write one program and attach one program to this trace point instead of attaching it to both, and therefore do ever so slightly less work, which is kind of important because your program is going to get run every time these trace points get hit. So you want to be kind of efficient if you can. It's very similar to before. In fact, it's you create a struct in pretty much exactly the same way as I talked about before. The only difference is, though, you'll notice that the file name is no longer a char star. It's now a data lock, and its size is 4 bytes, which is 32 bits, which is too small for a memory pointer. Well, actually what it is two 16-bit numbers. The lower one is the offset from the start of the struct to where to find the buffer, the information, and the upper 16 bits is the length of that buffer. And so from the start of the struct, you add the offset, and wherever it lands, that's where the data is going to be. One of the problems you have with BPF is BPF is very careful about only letting you access memory that you're allowed to access. So if you don't include anything beyond in the struct, anything that's beyond what's presented there in the format, then when you add to the start of the struct to get to the offset to get to where your buffer is, BPF can't tell that you own that memory. So what I've done here is I've added an unsigned char array of 4K, just assuming that a file name will be smaller than 4K, and that means that BPF will now let me access not just the members of the struct, but also the 4K of that unsigned char raw at the end of it. So usually the offset will point literally to the start of that buffer, but obviously you do the maths anyway to make sure. But now you can access it. So if you want to access non-syscall trace points, then you kind of need this. The other thing to note there is that file name has been copied from user space memory into kernel space memory, so it's much more likely to be available. And user space can't change that buffer while you're reading it. I don't know if you saw, but DEF CON 29 people presented phantom attacks, which is a talk worth seeing, which is where BPF or even Audit D, but based programs that are reporting events as they happen, like syscall events, what the point at which the kernel sees the buffer isn't the point at which your program is running and you're seeing the buffer. And so one thing could get executed and then user space could change that buffer and a different thing gets seen by your tracing program, which is really bad. Whereas here, this file name has already been copied into kernel memory. And so it is literally what the kernel is seeing is what you're seeing there. So another benefit to attach to a non-syscall based trace point, if there is one that's suitable. So when there isn't one that's suitable, you can actually attach using a K probe to any function in the kernel, pretty much, as long as it's not inlined, as long as it's a real function, you can pretty much attach to it. Now, what you'll need to do here is go to the elixir.bootlin.com, which gives you the source code for Linux kernels. It's a really, really great website. It lets you search for things. It lets you browse code. It lets you compare versions, all sorts of cool stuff. And find a function that does the thing that you're interested in. In this case, fork, right? I was interested in seeing what happens when a process forks. And so there's a function called __ shared fork, and I could attach a K probe to that. Now you can see that function itself takes two arguments, clone flags and a pointer to a task struct. And that will be the task struct of the newly forked process. So you can get your current task struct of the current process, the parent, and the task struct of the newly formed process. So what you get as a parameter, though, to your kprobe program is a pointer to this struct ptregs structure, which contains all the registers for your architecture. So this is x64, but if you're on ARM, for example, there would be ARM registers. And we know the calling ABI, application binary interface for Linux. So we know that the first argument is passed in register DI, and the second argument is passed in register SI. And then it goes DX, and then CX for the fourth one, and then R8, and then R9. So if you get your pointer to this ptreg struct, you can pull out those registers, and those registers will contain the parameters. So in this case, DI will be an unsigned long clone flags, and SI will be a pointer to a task struct. So that's really cool. So what you might find is that you don't really want to transfer a syscall, because you want the data buffer to have been copied before your program runs, so you can trust the buffer. You might not be able to find a trace point that's suitable for you for that purpose. So instead, what you can do is go through the kernel source and find the point at which everything stacks up. The data buffer has already been copied. The information you want is easily available at the start of the function as parameters, and then connect your kprobe program there, pull out the parameters, and then do the thing you want it to do. You can also, there's also a kret probe, which attaches to the return of a function. So that might be useful as well, because sometimes the parameter going in, like in this case, the task struct P, that task struct probably hasn't been populated. It probably gets populated by this function. So actually, you want to look at the task struct on the exit. So a kret probe would fire at the exit. So that would give you access to that task struct after the function has ended. So how do we go about inserting your code? Well, you pretty much write your function in C. You can use Rust these days, apparently. I haven't, but apparently you can. You could even write it in BPF machine code if you really wanted to. But for anything that's maintainable, mostly you're writing these things in C. Compile it with Clang. I believe GCC now has a BPF target as well, but most people use Clang. Excuse me. And that will compile to an ELF object containing eBPF code and all the maps and other sections that you need. And then you can insert that into the kernel using a library. So libbpf is the kind of traditional C-based library. You could, if you like Go, use Cilium eBPF, which you can get on GitHub for free. And I kind of recommend Go as being a good way of doing that. You can even use sysinternals eBPF that I wrote at sysinternals, which is a C-based library that lives on top of libbpf and simplifies a lot of the things, because there's a lot of like boilerplate and a lot of things you do over and over again, which I've simplified with that library. And there are other libraries available. So like Rust has one, for example. Go and find whatever suits you. That gets your program into the kernel and attached to the trace point or kprobe or wherever. And then whenever that thing happens, your code runs, write stuff out. Now, for debugging purposes, there's a trace pipe, which is in that same sort of directory. So sys, kernel, debug, tracing. There's a virtual file in there called trace pipe, and you can cat that, and you can write to it from BPF, and whatever you write will pop out in there. really handy for debugging. But for production, you really need a ring buffer, like I was talking about before. And then you monitor the ring buffer from your user space code that loaded the code in. Now, you can't run any function in the kernel, okay, from your BPF program. It's not like a kernel module where you can run pretty much any function. You can run no functions. But what you do have is access to BPF helper functions, which do a lot of the things that the kernel functions do. They're kind of abstracted for you and made safe. So we can access maps, we can update elements, we can look up elements, we can delete elements. We can access memory by using probe, read, and write, but only memory that we're allowed to access, and only memory that's actually paged in. And we can say write to the ring buffer with perf event output, or we can write out to the trace pipe with trace print k. Some more helpers that are kind of useful. We can get the current kernel time in nanoseconds since boot. Doesn't include the time it was asleep, so it's the monotonic clock rather than the boot time clock. But with later kernels, you can get the boot time clock instead if you wanted to. You can get the processor ID that you're running on. You can get the current PID and TGID. Now, bear in mind, in the user space, what we call a process ID, a PID, in the kernel is known as a TGID, a task group ID. And in user space, what we call a thread ID, a TID, in kernel space is a PID, a process ID, because the kernel assumes all threads are processes and they're grouped into thread groups. So it's worth bearing in mind terminology is ever so slightly different, so you don't get confused. It will only confuse you for the first 5 minutes, and then you'll realize what's going on. We can also get the current user ID and group ID of the process that we've interrupted, and we can get a pointer to the current task. And the current task is the task struct for the process that we've interrupted, and that contains all manner of stuff, like a pointer to the memory map where you can mine the memory owned by the process, a pointer to its FD table. So for the file descriptors it's got open, you can go and look those up and follow those and do things with that. Cred struct, or the credentials of the process, etc. So there's all sorts of really nice stuff, and you can find out most of that thing by looking at the elixir.bootling.com and find a struct, task struct, and have a look at its entries, and from there you can work out what you can access, we can gain access to. There's lots of other helpers, and so you can find those man BPF helpers, and that will give them. You can, I mean, a top tip that I use every day is if you type man and what you're trying to get a manual for into Google. Google's got all the man pages. You don't even have to type it in your command line. But what you'll find is BPF hasn't been particularly well documented in terms of learning. It moved really quickly over the last 4 years. So every time someone wrote something down, it went out of date in 6 months, which means that you'll find documentation, but a lot of it will be quite difficult to understand because it won't quite map to what reality you're experiencing. And it's very hard to take a tutorial from a year before another tutorial and read across, because the technology's changed, it's moved on. So one of the things you could do is go to the sysinternals GitHub, and inside the sysmon for Linux repo is a doc directory where I wrote up a whole load of stuff about how I wrote sysmon to help people in the community add to sysmon ultimately. That's mostly trace point based. I don't talk about K probes in there at all, but it would get you off the ground to go and have a look in there. And also in there, you'll also find an examples directory with 3 example programs, which are self-contained. Like each one's got a make file, it will make. And you can modify those in order to make them do different things and get a feel for what's possible and what you might be able to do with it. And they're described in that documentation. So if you want to get started, that's, I think, as good a place as any in order to quickly get up to speed. Read the code for eBPF. That's where you'll find the functions that eBPF offers. And equally, Cilium eBPF, if you're using the Go library to load your code. Have a look at the GitHubs and see what functions there are to do things, and that will give you a flavor for how to get started. Another thing you want to do is read the code of Tetragon, even read the code of Sysmon for Linux. They're both huge, I might add, but it's worth reading, and you'll see how we've gone about making these kind of things to monitor a variety of things. And we do have a docs.cilium.io, which will tell you all about Cilium and how that's been built. So if you wanted to do specifically network-based stuff, like moving packets around, load balancers, firewalls, that sort of thing in BPF, then the docs at docs.cilium.io will really help. Right, so that's the sell for how brilliant BPF is. Let's talk about how tricky it actually is to use. And I will say a reason for using higher level tools like BPF Trace or Tetragon, where you can make it do stuff by just configuring it, right? When you write your BPF program and you load it into the kernel using the library of your choice, the kernel will then verify your program before it will allow it to be attached. And the kernel verifier is renowned for being a difficult thing to satisfy. And if it's not satisfied, it will just drop your code on the floor. It will not run it, which is really annoying. So one of the things is size. Before kernel 5.2, you were limited to 4,096 instructions in your program. They're machine code instructions. So a single line C could turn into 4 or 5 instructions, perhaps. They lifted that limit to 1 million instructions in kernel 5.2, which is really helpful. However, the jump instruction for the vast majority of kernels, it only takes a 16-bit operand. So you can only jump forward or backwards 32,000 instructions. Now, if you're writing your program in machine code, that might not be a problem because you could structure your code accordingly so you don't have to jump further than that, or you could add trampolines so you could jump and jump again. But if you write your code in C, then you don't have control over that. And so what it kind of means is you're kind of limited to 32,000 instructions, even though you're allowed 1 million. Another thing is it checks that it halts within 1 million instructions processed. So the verifier will execute or simulate execution of your program and make sure that it stops, right? It will not allow you to have infinite loops or just run regardless, run forever or whatever. So you are allowed loops from kernel 5.3 onwards, but it will want to make sure that those loops end by simulating execution. And if it doesn't, it will complain about complexity and it will kill your program. Now, you can have function calls, but not if you're using tail calls before 5.8. So what's a tail call? Well, given the small size of program, you might have something that's more complicated than will fit into that size of program. So what you can do is you can chain BPF programs to BPF programs. They don't return, so it's not like a function call. It's like it literally replace this program with the next program, replace that one with the next program, and these are called tail calls. And you can chain up to 30 tail calls. But if you use tail calls before 5.8, you can't use function calls as well. So you're kind of limited. I found that function calls seem to be pretty much banned Maybe it's just the way that Clang compiles things. But whenever I try to use a function call, I get told that I've got a forward edge, which is verifier slang for you've done something horribly wrong. You're either looping or calling a function call, and it won't let you do that. So generally, you don't have function calls. What you end up doing is inlining all your functions, which bloats your code. So yeah, that's a kind of annoying constraint. And the other thing is there's no sleeping before 5.10. So I'll talk about that in a moment. You also it won't let you have any direct memory access. As I was saying before, you have to do all your memory access through BPF probe read and BPF probe write. And there's various flavors of those depending on which kernel you're on, sometimes divided between user space and kernel memory, but whatever. And even then it'll only let you access memory that you're allowed to access, which has certain constraints and controls around. It won't let you have programs that might have a null pointer in use, so you have to check for that your pointer is not null on every pointer that you obtain. It won't let you use certain helpers depending on the type of program. So there's lots of different types of programs depending on where you're attaching to. So a kprobe program attaches to kprobes, and you're allowed the set of helpers that are allowed for kprobes. Whereas SKB, which is a socket buffer, which is to do with networking, has a different set of helpers which overlaps. And then there's like C group programs which are attached to some of the C group kind of functions, and they again they overlap, but each one doesn't have all of them. So if you try and call a helper that you're not actually allowed access to, again the verifier will complain and will not let you run your code. So one of the things the verifier does when it's checking if you're allowed access to memory is it checks like how randomly bound your variable is. So if you had an array of 6 entries, for example, and you had an index I, and you assign something to index I of array A, and your I is unbounded, as in it could be any number, like then even negative, right? Then the verifier will spot that and it will say, well, you're accessing outside of the array. So what you could do instead is you could have an if statement in front of it, which says if I is greater than or equal to 0 and I is less than or less than 6, then do the array access. Okay. And that would work in a lot of cases, but it doesn't always work for reasons to do with the verifier. Sometimes the verifier is not so smart understanding that kind of logic. What it is quite good at is masking. So if you increase the size of your array to a power of 2, like 8, and then you mask your index with 1 less than the size of the array, which will be all ones on the right hand side, then it will limit I to between 0 and 7. And you might only be using between 0 and 5 because you only want 6 entries, perhaps, right? But the verifier will be happy that your index cannot be outside of the range 0 to 7, which is perfectly good for an array of size 8. And it's also that construction is a lot more efficient. It's 1 instruction to mask a register off, rather than 2 or 3 to do a compound if statement. The problem is that the compiler is quite clever as well, and the compiler has to rerun it with optimization turned on, otherwise it generates code that the verifier won't like. But when it's optimizing your code, one of the things it might do is optimize out your constraints, because it might look at that and kind of go, well, I know your index is never going to be greater than 7 or lower than 0, so I just won't bother doing that masking because I don't need to, because it makes no difference. So it might be smarter than the verifier, and then what you end up with is code that looks sensible in C, but doesn't actually pass the verifier. And when you look at the machine code using LLVM objdump, you can see that your constraint has been removed. Now, the trick to solve that is inline assembler. So you add your constraint back in with a bit of inline, and you make your assembler volatile, and that forces it to be at that exact point in the code. Another thing that happens that that's also really cool from an annoyance perspective is register spilling. So you've only got like 10 registers, and you're holding all these variables in registers pretty much for efficiency. Now, what might happen is Clang might reorganize your code for optimization purposes. And then what happens is it does the constraint where it masks off the variable, and then decides to do other things before it uses that index into the array. And when it's doing the other things, it might need the register that your index is in. So what it does is it chucks it on the stack, does its other stuff, and then it gets it back off the stack, at which point it's forgotten that you had masked that index. So now it thinks the index is completely unbounded. So another good reason for using the volatile assembler is that wherever you put that volatile assembler is exactly in the program where it will occur. So you can get the constraint as close to the array access as possible, which is something to learn how to do. I've not had that bite me recently, but if you look through Tetragon and you look through System for Linux, you'll see that that has bitten us numerous times, because everywhere you find some inline assembler, it's because this sort of thing has occurred. I say you need to check every pointer is not null before you use it. Typically what you might do is just, if a pointer is null and you're not expecting it to be null, that's a good reason to just exit out of your BPF program, because it means something's gone wrong. And that's a really simple construction that the verifier can definitely understand. So if it hasn't returned, it knows that the pointer must be valid. It might not be pointing to valid memory, but it knows that it's not null. Loops. So before 5.3, you couldn't have loops. You had to unroll all your loops, and Pragma Unroll will do that in Clang. And Clang's pretty good at unrolling loops. It can take quite complicated loop constructions and unroll them. But from 5.3 onwards, you're allowed loops. But the verifier has to check that they terminate. And so if you have a complex loop construction with a complex test case, the verifier will probably fail to verify it, because it won't be able to hold enough things in memory without using the stack in order to keep track of the state. So it's actually, so if you're going to use loops, you're pretty much better off sticking to like the really straightforward for loop that you see there, and then use break statements to get out of the loop if you have conditions that want to exit the loop early. And you can still unroll your loops from 5.3 onwards if that makes more sense. But as I say, once your programs start to get complex, then you'll start running a instruction count. So it might make sense to use simple loops. Page fault. So I was talking about sleeping earlier. So what normally happens with your program, and this can be a kernel module or a user space program, is if you attempt to access memory that's not paged in. So I'm sure everyone's aware of memory being paged in or not. Like the virtual memory space is bigger than the amount of RAM you've got in your machine, and some pages will get paged out into SOP space, for example. And you try and access some memory that's not paged in because it hasn't been used for a while, it's been paged out. Then what would typically happen is an interrupt would occur, which will take the context to a particular place in the kernel. That the kernel will then page the memory in, go find it wherever it is, page it into the slot, and then it will return from the interrupt to the start of the instruction that tried to access the memory. And then that instruction will run again for a second time and try and access the same memory. And at this point, the memory is paged in, and then you'll be given the information that's in there. Before 5.10 with BPF, you attempted to access memory, If it wasn't paged in, it just said no, gave you an error code, and the memory that you tried to read, the buffer you were trying to read it into, would just be zeroed. So that is kind of annoying. And so this is what I was talking about before about if you're trying to read user space memory, for example, it's often not paged in when you want it to be. So it's much better if you have to use syscalls, store the pointer on the entry to the syscall and read the memory on the exit of the syscall. But it's probably better to use a trace point where the buffer has already been copied into kernel memory, which is much more likely to be paged in, or attached to a K probe where the memory is literally being active, literally just being copied is a great place to go. There's a lot of helpers that aren't there. Like, helpers were written by people using BPF who are writing code for the kernel. They built the helpers they needed. And so there's a load of helpers that aren't available, specifically a lot of the string-based ones. There's no real path either. I think there might be something like that very recently, where you could take a path and get the kernel to resolve it to the actual path. So like, resolve symbolic links, all the dot dot slash dot dot slash dot dot slash type stuff. And there's no easy way of mapping from a dentry, which is a directory entry, or an inode, which is a place in the file system where you store a file, back to the actual path name. So you can do it manually by writing your own functions. And if you look in sys1, you'll find those functions. You might find them in TextCon as well, where you can take a directory entry which contains the actual file name of the file within the directory. And then you can get the parent dentry from that dentry, and then read its file name, which will be the directory name that contains the file name. And then you can go to the parent of that one and get the next directory, go to the parent of that one, get the next directory, and keep on going back until you get to the top of the tree, which are the various different ways of detecting depending on which distribution of Linux you're on. And as you're going, chain all of those bits of strings together with slashes in between them to make a file name. Obviously, when you get to the top of the tree, you're only at the top of the file system, and that file system might be mounted somewhere. So then obviously you then have to go and look in the mount tables and see if you're mounted. And if you are mounted, get the dentry for the mount point and add that to the front of your thing, and then traverse up those dentries to get to the top of that tree and repeat and recurse until you've got the whole path name, which is a pain to do. It'd be much nicer if you could just give a dentry to a helper and it gives you back the path. But unfortunately, that doesn't exist. So some things are very tricky. The perf ring buffer is interesting. So depending where you read the prototype for the function, for the helper function that puts stuff into the ring buffer, the size of the element you're putting in is sometimes referred to by U64, which is bigger than anything you're ever going to be using. Other places it's a U32, which seems a lot more like, 4 gig is big, but still you might want to put quite a bit of data in. Like a command line could be 128K, for example. So it's bigger, it's quite big. But whatever you put in there, when it gets through to the perf subsystem, which is where the ring buffer actually resides, it gets masked down to a U16, which is a 16-bit number, so down to 64K. And actually, it's not quite 64K because that includes some headers, and it's very difficult programmatically to work out how big those headers are. It depends on your compile options for your kernel, for your distribution, and various other things. If you assume 64 bytes of headers, then that would be a reasonable assumption. You probably won't find many more than that. So if you don't know about this, as I didn't, and I found it through trial and error, what happens is the ring buffer takes your entire chunk of data and puts your entire chunk into the ring buffer. But then it masks off the size and then advances the pointer by the 16-bit masked size. So if you had if you put in exactly 64K, including the headers, it gets masked to 0. And the pointer doesn't move at all. In fact, it doesn't even put it in at that point because it goes, oh, the size is 0. Why am I bothering to put anything in it? But if it was 64K and 8 bytes, it gets masked to 8 bytes. The whole 64K and 8 bytes goes in the ring buffer. And if you read it out in user space, it'll all be there. But the pointer will only be advanced by 8 bytes, which means the next thing you put in the ring buffer writes on top of the stuff you've put in there and corrupts your data. And I actually reported this to the BPF mailing list and had to include code to demonstrate it because people hadn't seen it before. But it turns out it's not a BPF bug, it's a perf bug. So and finding the size of the headers, as I say, isn't particularly easy. So it still exists and it hasn't been fixed. So you have to be aware of it. As I say, you might want to put 128K in there. You might want to put a whole command line in there, for example. So the answer apparently is to break things into chunks. And in actual fact, KP Singh, who works at Google, gave me the advice that if you've got a big event that you want to send to user space, then actually it makes sense to chunk it up into like 4K chunks, for example, because if the ring buffer is full, which can happen if you're sending a lot of events in and user space is very slow at getting them out, then your event just gets dropped on the floor and it never makes it to user space. And so if you only deal with full size events and an event gets dropped, then you in user space, you don't even know that event's been dropped. I mean, there's a counter that will tell you how many events have been dropped, but you don't know anything about that event. If you've broken it into 4K chunks and you throw it into the ring buffer, more of those chunks are going to, some of those chunks are going to get through to user space, even if you fill up the ring buffer. It's going to be much more efficient use of ring buffer. And so you could number those chunks, you could reconstruct them in user space, put them all back together, and you could detect that a chunk is missing. But the thing is, you still know the event happened. You still might know that it was an execution event. You still might know the file that was executed. You might know the user ID that executed it. You might just not have half of the command line. Well, that's much more useful than the event just never getting there in entirety. So it actually makes sense to chunk things, and therefore this arbitrary 64K-ish limit isn't really a problem in practical terms if you were to take that advice. Right, finding things in the kernel is funny, right? So depending on the configuration options to your kernel, and depending on which kernel, and depending on which distribution and what patches they've applied to the kernel structs are different sizes and shapes and are laid out in different ways. So, which makes it very hard to read an element from a struct unless you have the kernel headers for the system on which you're running. Now, if you're running on your own system because you're building tools to help your reverse engineering, then you have all those kernel headers. Just use them, it'll be fine, right? But if you're building production software to go and run on other people's machines, then you don't have a clue. So instead, what you need to use typically is BTF. That's BPF type format. It appeared in kernel 4.18. And it was enabled by default in Ubuntu 20.10, which I think was the first distribution to enable it by default. So before that, it exists, but you'd have to recompile the kernel to enable it, which is kind of annoying. What you could do instead is use Cilium eBPF, which has another way of accessing BTF data. You could use BTF Hub from Aqua, which, given the kernel version, it will go to the internet and find the BTF for that kernel version, assuming it's a known kernel version, like it's a published kernel from a distribution. And then that BTF information will be used at the point that your program is loaded into the kernel. And what it does is it remaps all of your accesses into structs so that they go to the right place in the struct for the kernel you're running on, rather than the place in the struct it would have been at on the machine you dev'd it on. The other thing you could do is use the approach in sysinternal's eBPF. And I sort of mentioned that partly because I wrote it, but also because it's kind of cool. What that will do is it will, if there's a file of offsets that describe how to access certain members of certain structs, then it will use that, and it will use those offsets in the BPF program. It doesn't reorder the code or anything. It uses it in a function, so it knows how to use that information in BPF to find the right places in the structs to get the information. If that doesn't exist, then it looks in a massive database of published kernels that I ship with sysinternal's eBPF. And that's a similar thing to BTF Hub, except it's only the offsets that I needed, right? But you could extend that to other offsets if you needed to. I actually got those offsets from Project Frita in Microsoft, who have offsets for all published kernels, for a similar thing to BTF Hub, but for a different project. But if that doesn't exist, or your kernel's not in there, then what it does is it uses BPF to do memory forensics on the kernel memory in order to work out where things are. So imagine that, you know, your program that's loading your BPF program, well, you know everything you need to know about that program. You know what it's called. You know it's COM, for example. Well, you know it's PID, right? That's the first thing you definitely know, is it's PID and it's TID. Well, what you could do is you can get the task struct using the BPF help that'll get you a pointer to the task struct, and you could dump 4K of memory from the start of the task struct to user space, and then user space can search through that code looking for that PID and TID, and when it finds it, you now know the offset to the PID and TID from the start of the task struct. Store that offset because you might want it later. Let's say you know the COM, so which is the short version of the program name, so you can search through it for that. You can recognize pointers because pointers into kernel memory are very recognizable. So you know roughly the layout because the layout doesn't change that much. So you could move forwards and backwards looking at the pointers, expecting there to be a pointer to like a cred struct, for example. Well, you could fork your user space program and drop your creds to a specific UID and GID that are quite random numbers, like 1, 2, 3, 4, 5 and 5, 4, 3, 2, 1, for example, right? And then you could dump memory from each of those pointers that the task struct is pointing at and search through them until you find your UID and GID, at which point you can be quite confident you found the cred struct and therefore the pointer to the cred struct, and therefore the location of the UID and GID in the cred struct, and so on and so on. There's lots of things that you know about your own process you can use to then find your own information in the memory that your own program is pointing to. The way I trigger the BPF program is I just call a syscall and attach to that syscall. So I used uname, which gets you the system name, just as a lesser used syscall, really, and attach my BPF program to that. And then when it runs, I can check the process ID by sharing that through a configuration map, which is shared between user space and the BPF program. So my BPF program can get that configuration map, it can pull out the process ID, it can check the process ID against the current process ID, which it gets from a helper, make sure it's actually my program that's been interrupted, and then it can do all of these clever things. And using that, you can then build up a set of offsets to the things that you care about. So yeah, it's not massively scalable, and it does have some bugs on Red Hat, but it works pretty well on Ubuntu. or it did. I don't know if it still does. But it was another way of finding stuff out when you haven't got BTF available. Of course, what you could do is just demand that your customers run a BTF enabled kernel, and then that solves a lot of these problems. But yeah, finding the size and shape of structs is quite tricky. Licensing is really interesting, right? I'll start by saying I'm not a lawyer, so do go and get your own legal advice. One of the things that's really interesting, right? So a lot of the BPF helpers are GPL2 licensed. Other ones aren't, but most of them are, and most of the good ones are the ones that you want to use. So ultimately, because you'll be calling these BPF helpers that are GPL2, it will make your code GPL2 for the code that runs inside the kernel. It's the BPF code. And the way it does that, and this is, I think, unique, is that your BPF program has to, by virtue of the verifier checking it, state in the ELF binary what license your code is licensed under. And you can dual license things, but if your license doesn't include GPL2 and your code tries to access a GPL2 helper, the verifier will prevent your code from running. So, normally in the world, we write what license something is in a license file, in a README or in some documentation somewhere. In BPF, you have to state in your BPF code what license it is licensed under. Otherwise, it won't be allowed to run. And if you don't state that it's GPL2 at least, then you don't get access to the helpers that you need. So your BPF code is almost certainly going to be GPL2. Now, libbpf and system terms of eBPF, which is built on it, are both LGPL 2.1, which is allowed to load a GPL2 program into the kernel, and you can attach any, because they're libraries, you can attach any user space program to them dynamically under any license you like. Cilium eBPF is MIT, but your BPF code will be GPL2, which means that if you sell it or provide it to somebody as binary code, they can ask for the source of your GPL2 code, your BPF code, which is kind of a interesting place to be. I spent a lot of time talking to Microsoft lawyers in order to understand this. But yeah, get your own legal advice. And then finally, we're almost at the end. I'm going to very quickly talk about vulnerabilities to do with BPF. And I'm not going to go into any more detail than what's on this slide. But basically, if you go to any CVE database and put in the key, the code BPF, you'll find a load of CVEs, right? Most of them will be in libbpf, and you don't really have to worry about them, to be perfectly honest. Yes, some things weren't bounded particularly well. They're not very interesting bugs, like who massively cares, okay? But there are some interesting bugs in the verifier, and I urge you to go and search for them and read the write-ups about them, because they are some of the most interesting vulnerabilities and exploits I've ever come across in my career. I haven't discovered these. I'm literally reading the work of geniuses here. But imagine this, right? So the verifier verifies your code by simulating execution and following the code paths. If you have an if statement based on a variable, like if this variable is 1, go this way, and if this variable is 0, go this other way, and the verifier works out that that variable can only ever be 0, it will only check the path for that it would follow if it's 0. Because what would be the point in checking the other path if it's inaccessible code, right? But there's a way of getting a 1 into a variable when the verifier thinks it's a 0. And that means that it verifies the 0 path, which is all very nice, friendly code that doesn't do anything dangerous. and all of your dirty, nasty, illegal memory access and illegal BPF helper access can all be in the one path. And in practice, that's the path that gets taken because you've managed to get, because that variable actually holds a 1, even though the verifier thinks it holds a 0. You can also use that 1 to continually increment yourself into places that the verifier thinks you're not incrementing. You know, if it thinks you're adding a 0 over and over and over again, it maintains that the pointer is still where it was. But obviously, if you're actually adding a 1 over and over again, then obviously your pointer is actually increasing. And you could do the same thing. You could left shift that 1 bit through the variable and make it a much bigger number and then add it to a pointer. And again, the verifier still thinks you're adding 0, but actually you're adding a very big number to your pointer. And therefore it'll allow the memory access when it should probably prevent it. So as I say, it's a really interesting bug. A few different people have done work in that area and have written blog posts about it. Go and have a read. It's quite interesting. It doesn't make BPF vulnerable. So the verifier was written mainly with safety in mind. Like, it's protecting you from yourself, from writing code that you shouldn't be writing because you've accidentally done something silly that could crash the kernel. It's not really built for security to prevent nefarious programs from running. You pretty much have to be root to load code in. Those actual vulnerabilities that were exploited because there's one program type where you don't have to be root or have capsysadmin in order to load the code, and therefore you could elevate your privileges by being a lowly user, exploit this verifier, get a program into the kernel. It runs, it exploits this verifier bug. It uses that to then overwrite memory in your task struct to change your UID to 0, and then your process is now root. So I say really, really cool vulnerability. But BPF is either on or not on. It's either available or not available in your kernel, and it doesn't become vulnerable just because you're running your own BPF programs to look for things and audit things and store things. It's either vulnerable or it isn't. The only solution is to upgrade your kernel, or apply the patches to your kernel. So it's not a good reason not to run BPF. And in actual fact, if you turn off BPF, you lose so much functionality that I don't think anybody is, and I don't think anybody's recommending that. So as I say, it's more of an interest perspective to go and have a look at that vulnerability. So with that, we're at the end. There's a complimentary slide of a whole load of organizations that trust Cilium to do their Kubernetes networking at scale. Usually the first question is can you put those links back up? And yes, I can, including a link to where you can get these slides if you want to go over the slides yourself. And with that, I am there. Are there any questions?
Yeah, thanks a lot. Thanks a lot, Kevin. Very, very interesting. We don't have any questions in the YouTube chat, but Dave, Craig, Angie, are there any questions from yourself?
I'll probably go with my usual line of questioning. Kev, I will apologize ahead of time because I'm sort of like your basic programmer. I'm sort of more of your bash scripter and your PHP coder. So I'm a little out of my depth when it comes to this stuff. But one of the things I always try to look at is, with C programming, it's very easy to sort of shoot yourself in the foot. And it does look like the verifier is designed to try and pick up problems before they actually become problems. And I think, is it Rust does a similar sort of thing where it tries to sort of protect you and stop you from doing stupid things?
Yeah.
Do you sort of see that as like what will become the status quo of we're going to actually try and to actually stop the developer from being able to make mistakes.
Yeah, I think a lot of high level languages or modern languages are moving in that direction, and it makes a lot of sense. I love C. C was one of my first languages. Actually, I went from basic to Z80 machine code, and C came a little bit later in my career. But it's still, my language of choice mostly. Although nowadays I program a lot of Go, which is has a lot of these similar kind of protections built in. It makes sense. We want to stop crashing things and creating security vulnerabilities needlessly. So yeah, I definitely think that's the direction things are going in. And the verifier does actually make you write better code. You end up writing simpler code that is easier to reason around, and therefore you're less likely to put bugs in. And if you have put bugs in, they're easier to find. And you do end up making your memory accesses much more safe as a result. So I would say it's kind of a good thing, and that probably is the right direction.
Because I see the C language as being useful for people like you, as in this is the stuff you live and breathe and you need all the detail in that. But I'm also thinking of the typical developer, the vast majority of developers who have a particular program they need to write. I'm sort of going, please don't touch C. You don't know what you're doing. In the same way as I do not know how to write C, and I should never touch it ever. So I'm looking forward to sort of seeing these things play out. And do you sort of see now that you've got the verifier sort of protecting against some problems? I think you sort of mentioned about acceptable memory access was one of the slides you came up. Do you sort of see any other areas it could sort of start protecting or looking after in the future, or do you think most of them are covered already?
I mean, the verifier is pretty comprehensive in the kernel. It's at the moment it's limiting you to only safe things. The only way that vulnerability exists is because of a bug in the verifier. The verifier gets smarter with each version of kernel that comes out, and therefore it allows you to do more things, as in more things that would feel more dangerous, because it's smart enough to understand if they're dangerous or not. Yeah, I mean, if you look at .NET or C# for example, you're kind of constrained into only really doing safe things, which is pretty cool. I mean, I will say, like, when in a previous job I wrote some cracking software for HiTag 2 RFID, and I needed speed, unfortunately, and C definitely gives you speed, and a load of that code had to run on a GPU, like a graphics card, and you can, I mean, I think you can pretty much only write that stuff in C. Yeah, like, it still has its place, but I mean, from a security point of view, I'll be happy when C is gone.
Yes.
but the whole of the Linux kernel is in C, so don't expect that anytime soon.
Yeah, because I sort of got the impression that, and again, I'm talking from a position of ignorance, is that Rust sort of tries to do C, but is basically using that same principle of we verify it while we compile it, and therefore the end result isn't that different to the C programming, is my understanding. Indeed. And to be fair, like, Go is almost as fast, although that's got a garbage collector, which Rust doesn't have. I mean, I've not used Rust yet. I hear that it's a bit of a mouthful to write, whereas Go looks a lot more like C, and feels a lot more sort of logical and comfortable, and you can get going quicker. But yeah, exactly. I mean, this is it.
we're going to have more and more of this, I think, as things go on.
Yeah, brilliant. I'm glad to see it happening, and thank you very much for sort of working on this, because it's, so I get annoyed with, we keep on making the same mistakes over and over again, and if we can start having programmers not make the most basic of mistakes, they're the basic mistakes I would make because I just forget.
We all make them. I mean, that's how almost every vulnerability between the start of the internet and now has existed, is because people have made those mistakes. So the worst ones are the ones where you don't know you've made the mistake, and the program still works until someone does something really annoying.
Yeah, for me, it's I've got a little bit obsessed with about injection vulnerabilities. So you talked about going over with the COVID lockdown and stuff. I got a little bit obsessed with that one, because some Google engineers pointed out a really interesting thing, which was, if a program can identify that a string is a developer defined string, then it's not possible for that developer defined string to contain injection vulnerability. And you go, oh, that's actually a really simple observation. Just a single flag on a string, just to say this is developer defined or aliteral, and anything else. And then you use that with your SQL. If your SQL is only written by a developer, cannot contain injection vulnerability. And the difficulty comes in when you start talking about like HTML, in which case you say, well, a library should be doing the templating stuff. So you give the template as HTML to the library, and then you give the user values to it separately. And the library, who knows about everything about HTML, can do all its magic and make it work. So that's my little project.
Yeah,
and I'd like to see injection vulnerabilities disappear entirely, in the same way as like this verifier seems to be sort of attacking like the memory safety problems. So yeah, anyway, sorry, that's my tangent. Dave, have you got anything?
No, I've made lots of notes. I'm not doing much coding at the moment. I used to do C, show my age, but I used to do it on the Amiga. So
cool.
It's a while ago now. So I don't really use it these days, but it was very interesting. Yeah, like I said, I bookmarked quite a lot of things, and I'll grab your slides and I'll go through it again. But yeah, thanks for coming on. It's great.
Yeah, no worries.
Yeah. Back to you, Katie.
I think Katie's muted.
Yes, yeah.
Yeah.
Oh yeah, I was trying.
Try again.
Typical, trying to speak when muted. Yeah, thank you very much. Thank you very much, Kev. So I'm going to stop now the streaming, and I think we are going to wrap up now.